Hello everyone. I'll be teaching statistical thermodynamics as a part of this course Thermodynamics and Statistical Thermodynamics for Biology, and I am Sanjeev Senapati from IIT Madras. And for this part of the course, the reference books what I'll be following are Statistical Mechanics by Donald A. Macquarie and Molecular Modeling, Principles and Applications by Andrew R. Leach. So, before we go to statistical thermodynamics, let's look at what we mean by classical thermodynamics. So, as you know, classical thermodynamics is also called the continuum thermodynamics. And if you look at the name thermodynamics, so thermodynamics, as the name implies, it essentially talks about dynamics or the flow of heat. Dynamics is nothing but the flow and thermo is nothing but the heat. So, thermodynamics talks about flow of heat, and if you look at the first law of thermodynamics, it basically gives you the relationship between heat, work and change of energy in a physical, chemical, or it could be a biological system. And this is the first law where you see the change of energy of a system is equal to the heat supplied to the system minus work done by the system on the surrounding. So, how statistical thermodynamics is different than the classical thermodynamics? As you saw, the first law, thermodynamics provides connection between many properties. There are many other properties you have come across in the first part of this course. One of the equations what we will be using in few minutes is delta G is equal to delta H minus T delta S. So, that expression basically gives a relationship between free energy, enthalpy and entropy. So, thermodynamics basically is providing the connection between many properties, but it does not provide interpretation concerning the relative magnitude of those properties. It doesn't say why delta H is so much, why delta S is so much, why the heat, why the work done by the system is so much, and so on. So, this in fact is both the power and the weakness of thermodynamics. It is a discipline where it does not need to recognize the existence of atoms or molecules in the system, and here enters the statistical thermodynamics. Statistical thermodynamics, in the other hand, assumes that the system is composed of molecules and atoms, and it calculates and interprets the thermodynamic quantities from the molecular point of view. Thus, thermodynamics and statistical thermodynamics, they treat the same systems, but their goal is different. So, in nutshell, if we have to define the statistical thermodynamics, we can say statistical thermodynamics is that branch of physics which studies the macroscopic system from a microscopic or molecular point of view. So, here macroscopic system, by that I mean the properties what you measure in laboratory. For example, pressure, volume, free energy, change of energy and so on and so forth. So, how those macroscopic quantities can be obtained from microscopic information of the system. In other words, the goal of statistical thermodynamics is to understand and predict macroscopic phenomena and also calculate the macroscopic properties from the properties of the constituent molecules or the atoms that make up the system. Let's take an example. We have a protein, and let's say this is the conformation of the protein. We say this is P, and we have a ligand L which binds to this protein to make the protein ligand complex, PL complex. Now, what will be the delta G of ligand binding? So, this delta G binding you will be getting from thermodynamic expression delta H minus T delta S, where delta H is change in enthalpy and delta S is the change in entropy. So, this is the thermodynamic relation what you got to get the change in free energy due to the binding of the ligand to the protein. But what is the what's the magnitude of delta H, magnitude of delta S? The classical thermodynamics does not tell you that. Now, statistical thermodynamics comes. So, I am writing another expression from classical thermodynamics. What you have come across is delta H, as you know, is delta U, change in internal energy, plus P delta V. So, now statistical thermodynamics can explain why delta H is this much. Statistical thermodynamics now considers this particular protein is composed of amino acids, and each amino acid is composed of many atoms, carbon, hydrogen, oxygen, the peptide bond, and so on and so forth. It also considers that my ligand is having the atoms that made up this ligand molecule. So, now statistical mechanics will calculate this delta U as sum over I, sum over J, U Ij. So, this Uij is basically defining the interparticle interaction. So, Uij is basically the interaction of ith particle in the ligand with the jth particle in the protein. So, delta U is obtained from statistical thermodynamic law, which says that the interparticle interactions between the ligand and protein, sum them up. If you sum them up, you get the total U of the protein ligand complex. Likewise, if you want to get the entropy, so you basically calculate from statistical mechanics the change in degrees of freedom of the ligand and protein due to the binding of the ligand to the protein active site. So, as you see, both entropy and enthalpy you are getting from statistical thermodynamics, and those magnitude you are putting up in this expression of thermodynamics to find out what is your delta G binding. So, both thermodynamics and statistical thermodynamics, they are applied to the same system, but for different goal. Okay. So, now we need to get a few basic concepts of statistical thermodynamics, and the basic concepts of statistical thermodynamics can be presented in terms of few quantum mechanical properties, such as the energy states, the degeneracy, the wave function, and so on. So, from my this statement, it might appear that you need a quantum mechanical quantum mechanical knowledge, but that's not the case. Soon I'll show that a satisfactory version of statistical thermodynamics can be presented by using only a few quantum mechanical ideas and results.